Welcome to this lecture called The Journey of AI in Games. It will be a long one, so I'll try to be quick. So let's start with the agenda first. Obviously, I'll introduce myself, and then we'll embark on a journey to explore how AI worked in games in previous years and how it works in recent times. And exploring these implementations, we will also try to better understand how it can improve given the recent advancements of AI and what can be used to kind of incorporate this new tech and make games even better. Or if we can't do so, or even if we need to do so. So this is kind of the philosophical part of the lecture. So first, a bit about me. My education is in computer science. I have a bachelor's degree and a master's degree in computer graphics, both acquired at SOFIA University, St. Kliment Ohridski. 4 years ago, I also studied in the Game Dev Advanced course of Arc Academy, where I already knew how to program, obviously, but I wanted to learn more about modeling, VFX, animation, game design, level design, everything that was missing from the puzzle, and I wanted to become a generalist and sort of make my own games. But the professional experience, I have like around 10 years of professional experience as a programmer, both in standard backend software engineering and in AI development. But since games were always my passion as a kid to play them, and at around 7th grade, I also started implementing some games with my brother. So it was only natural to, at some point, transition to a more professional environment. And I started a job as a multiplayer programmer at a shooter called Bulletville. It's a hero shooter like Overwatch, but third person and much crazier. Involves a lot of parkouring, a lot of crazy abilities. So the networking and the multiplayer was very, very hard to code. So I was like a low-level networking engineer there. And after that, I continued my journey professionally as an AI programmer, and which I'm currently doing at Bloober. And we make Silent Hill 2 remake, woo, which is one of my favorite games as a child when I played back in the 2000s. And I'm also co-founder at Awkward Pixel Indie Game Studio with a bunch of friends. And some trivia, I like extreme sports and I competitively compete in Street Fighter 6 on a European scene. Right, I have a clicker. So first, a little bit of background why I decided to do this lecture. It was because the organizers forced me to do it, but even more so because I constantly hear some misconceptions about AI. And mainly in AI in games, since we were currently speaking about games. So these exaggerations or misconceptions for AI in general translate into games, and many people think that a lot of breakthroughs will happen in very little time for games as well as they did for machine learning and AI in general. So there are like two types of people. There are some skepticists that can probably tell you that, okay, AI may probably recognize cats, and there are some people that tend to exaggerate, and they think that Elon Musk is an advanced form of AI and he'll overtake the world. So it's good to clear out the basics and to see what AI exactly is. And first, I want to say that AI is old news. It's not new. It's not a recent development. It dates back to the 1950s, and the mathematical models were laid out even in these years, but there were a lot of hardware limitations. And now we have the tech and recent improvements in these algorithms that can apply to today's standards and actually achieve amazing things like ChatGPT. But the mathematical part was already there much longer ago. And you've been using AI on a daily basis. It's currently trending to use ChatGPT and say that this is AI, but you actually used AI in the past in a lot of forms. Like if you watch videos on YouTube, and the machine learning algorithm learns your patterns and can recommend other videos. So these are like recommendation engines, email spam filtering, and others, and Google searching, obviously. So yeah. So why is AI exploding now, and how will this possibly translate into games? First, as I said, computational power. Every 12 to 24 months, we double our computational power. This is called Moore's law, and now we're at a point where algorithms can actually use this big data that we have and actually run neural networks and infer some good results like ChatGPT does. Another reason is that we have much more labeled data. Back in the past, if you want to design some algorithm that recognizes cats, you need to go and annotate your data and watch pictures of a cat and annotate it, and then train the algorithm to recognize cats. But now this data is massively available. We have like 175 billion million megabytes of data that is annotated currently, and most of the times easily accessible. And the costs for training are greatly reduced. Now, even indie developers can rent their servers at Amazon and train their algorithms there and not actually buy this hardware. And a lot of companies, as they see in the progress in ChatGPT and other tools, they tend to invest a lot, and Netflix, Google, Facebook are constantly competing. So this also makes the algorithms much better at a much higher pace. And yes, now, as I said, there are a lot of advancements and training optimizations that are done, which led to actually the miracle that ChatGPT is. So, but still, let's answer this basic question real quickly. So we learn what AI is or what AI is not, so we can think about how it is implemented in games and how it could be implemented using latest advancements. So probably you know about, probably you remember when Mark Zuckerberg said that AI is like a smart toy that if you show it a picture of a puppy, it will say that it's a puppy. If you show it a picture of a kitty, it will learn that it's a kitty. So maybe you don't remember that, don't remember him saying that because he never did. ChatGPT did. When I asked him to explain AI to me like I'm 3 years old. But on a more serious note, artificial intelligence is a group of algorithms and programs that can behave and reason like humans. And there's more specialized field called machine learning that we already spoke about. This can cluster data, give recommendations, and all sorts of algorithms like this. And we have the deep learning, which is what ChatGPT uses. It's a specialized LLM model, a specialized neural network. And why do we call it neural networks? Because it's how our brains are actually formed. We have neurons in our brain, and these algorithms kind of simulate these behaviors and how we learn as people. So these algorithms learn as we do. Well, again, the example which showing the picture of a cat, and it can quickly learn if you show him like tens of thousands of pictures of cats. So how many people do you think that games use machine learning? How many think that they use deep learning? Good. You're right. We don't use any of this. In fact, the AI in games is less complex, or should I call it dumber, to the point that even I won't call it actual AI. And I develop dumb AI all of the time. I do it on a daily basis. I go to work, I develop some dumb AI. After that, we have playtests and people like it and say, yeah, we like this dumb AI, but actually it gives the fun factor to players. So why is that? Why don't we use these more advanced systems that I already spoke about? There are historical reasons, so let's dive into this and hopefully explain if this new tech that's coming in place can hopefully improve what we have in the past. So how was AI used in older games? You can think, before 2000s, you can think of Nintendo games or Sega games. Very, very simple games. So most of these games use something called the rule-based system. And it consists of several things. I will list them now as theory, but even if you don't get everything now, the next slide will have a lot of examples, and I'm sure you'll get it. So a rule-based system has some conditional logic. This is like the if clause. So if some conditions are met, some action is executed. And in order to pull this conditional logic and ask, so is this condition met? We know the algorithm needs to know a lot about the world, and it has to have some knowledge representation of the world that it lives in. These systems are practically easier to debug than neural networks or machine learning algorithms. They are very transparent. So if you open Super Mario's code, it will look like a big chunk of code that has if else, if else, if else, if else. And it's kind of daunting, but once you get to understand it, you can easily debug it. Whereas if you wonder why a certain video YouTube is not recommended, it's very, very hard to debug such an algorithm. So developers thought, why not use something simple that can also lead to good results? But it has the problem of scalability, and we'll show how games evolve to solve this problem. But first, examples. Examples of a rule-based system. So everyone knows this game. And if we go, again, in the bullet points, the knowledge representation is in this system is all the knowledge for the world. For example, we have two enemies, Goomba and Koompa Troopa. They both have a lot of knowledge about the world, but one of them uses this knowledge and the other doesn't. So the Goomba doesn't use the knowledge about is there a ledge, and it just goes straight and falls down. But the Koopa Troopa uses this knowledge that there is a ledge and uses it to turn around and not fall. So this is kind of the conditional statement, is there a ledge, which is pulled from the knowledge representation, and the action is turn around. So this is like the most basic example. But if we go deeper into this, there are more complex examples, such complex examples that I didn't even understand as a kid. Is that this guy called Wakito is actually a turtle in a cloud that throws spiky eggs. And still, even if it's very hard to grasp, as a kid, even if you don't know what a rule-based system is, you can kind of guess what's happening under the hood. So this guy is kind of following you around. He will never stop, at least some certain other condition is met. And he'll, from time to time, throw these spiky eggs. So even as a kid, if you don't know what a rule-based system is, you kind of guessed what's happening. And a more advanced example is the Hammer Bros. They're like the most advanced enemy in Mario, which track a lot of things, so pull a lot of this knowledge about the world, knowledge representation, like is the player to the left or to the right of them? Is he close enough? Should I change the parabola that I throw these hammers? Should I go down? Should I go up? So they were like the most annoying ones because they were kind of advanced at that point. And now, what you might think is happening at this point of time in the industry is something like this, and you won't be you'll be quite right. This is exactly what happens, but it was fun at the end of the day, and we'll see why later. Now, what if a rule-based system is not challenging enough? What can an AI do? Of course, it can cheat. So here we have an example from Street Fighter 2, one of my favorite childhood games. And we can see Gaia on the right doing the flash kick, which is he's not supposed to do it while standing. He needs to crouch for a second and then execute another input to do it. But the AI is able to do it while standing. And I cannot tell you how many hours as a kid I lost to understand how can I do this move when the AI does it while standing, and I can never really guess what I need to do. So later on, when the internet became a thing, I found this and I started hating Capcom. So let's go to a more recent times, like in the 2000s. You can think of games like Unreal Tournament, Quake, tree, and the likes. So people thought, so this is just a pile of if-else statements. What can we do to make more complex systems? If we want to make a bot for a shooter, and we have this huge pile of if statements, it's hard to manage. So what can we do about it? And as developers like to do, they go into the mathematical models and try to copy stuff and just plagiarize. And they found that mathematical model, again, designed in the 50s or even earlier, called finite state machines, might be useful to give more structure to these if-else statements and put the AI in different states. So this term sounds fancy. We'll follow the same pattern. I'll first explain it as text and then give you an example so you can better understand it. So what is a finite state machine? Obviously, it has states, so the AI can be in different states, like attacking or retreating or patrolling. And there are transitions between these states while certain conditions are met. Very much like so when it was for Super Mario. If certain conditions are met, we can transition from one state to another. And in these states, the AI can do a lot of actions. So if it is in a combat state, it can strafe, jump, shoot, and do various checks. But there are like a bunch of actions that happen only in this state, and they're encapsulated in this state. And these systems are good because they are deterministic. So if you are in a one state and certain conditions are met, you only proceed to a certain state. There's no ambiguity in that sense. So I'm sure most of you played this game called Quake 3 Arena, and it used for their bots, which were praised at the time for being one of the most non-cheating, better bots out there. It used finite state machines, and it's good that the guy who invented them actually made a book about it, and there is a thesis about it. So I took this right out of his book, like developers like to do, as I told you. We like to copy stuff. So you can see here that the circle things are the states, obviously, and I have a pointer, by the way. Yeah, so these are the states. Here we have 4 states, and these are the transitions. And under some conditions, we will transition from one state to another. So let's say the bot's default behavior is to gather items, and he will be happy about it. But at some point, the condition is met that he sees an enemy. That can be an AI, another bot, or the player. So he transitions to this state and starts attacking. And inside the state, he can do a lot of actions like, as I told you, like shooting, strafing, jumping. And under some conditions, let's say its health becomes critical, it can transition to the retreat state. But I want you to notice that it doesn't make any sense for the AI to gather items, then attack, and then go directly back to gather items. So this is where the determinism comes. So you cannot reach any state from any state. There are certain rules that need to be met. So let's say the AI is now in the retreat state, and it sees that it loses to the player, so the player is catching up. It can decide to go back to the attack state so as a last resort to kind of try and defeat it when everything else fails. But if there's no threat anymore, if the player doesn't see the AI, then it can go back to gathering items. So I had to use this meme once more because, again, these transitions that we have are also looking more like if-else statements. It's just that it's much more organized for developers to create more complex systems in such games. So it was a good approach, and it kind of yielded good results, but it's, again, kind of tricky to manage. So how this thing evolve? So again, developers went to the drawing board and started copying other stuff. And they figured out there's another mathematical model that's, again, developed a lot while ago called behavior trees. And they said, why not try to use it to organize our if statements more? And what is a behavior tree? I'll go quickly again as text, and then we'll even do a live demo. of a game that I worked on, a small project. And even if you don't understand this directly, it will make sense afterwards. So they are very similar to finite state machines. The only difference here is that states are now becoming branches in terms of this terminology. The transitions are now called edges or connections. The actions are now called nodes or tasks. And they are hierarchical in nature, which helps with organizing the code base. But for the player, it's probably transparent. So it's not very, very different than finite state machines. So if I show you a game, now with bots, you probably cannot tell me if it's finite state machines under the hood or behavior trees or any sort of similar organization of code. So if we want to transfer the example from Quake tree to a behavior tree now, as you can see, the states are now branches. So this is one branch, this is another branch, this is another branch, and they can have multiple nodes or tasks. Previously, they were called actions. And the behavior tree is evaluated from left to right. So it tries to go to the retreat state or branch. If certain conditions are not met, it will try to do the next, and most probably at the start of the game, it will land in this state or this branch, and we'll just gather items. But if something more important happens, if, for example, an enemy appears, it needs to break out from this state. So in finite state machines, there was a direct connection here between the two, but now this branch can override this branch. So each of the left branches can override all of the branches to the right. So there's certain type of priority here, like they're sorted in an important manner, in a manner of importance. So the retreat is the most vital one. So even if the AI is currently attacking, if his health is low, for example, it can override this stage and go directly into the retreat, which is what most people will probably do as players. If they feel that they are losing the battle, they'll try to retreat. So gathering resources is not very important at that point when you try to save your life. So I will be brave enough to try and do a live demo now, and wish me luck. This is Unreal 5.1, and this is, as I said, a little side project of mine. I designed these two little bots that can fight against each other, and they're mainly using ranged combat. Can we dim down the lights? Is there a way? Okay. We can live with this. So this is the scene. When I hit play, these bots will start fighting against each other. But what's more interesting is the behavior tree. And it looks pretty much like what I showed in the presentation. We have a patrolling branch, we have an investigation branch, an attacking branch, and a retreat branch. And they're sorted by importance. So at the start, when I hit play, we can observe how these two AIs behave. And I'll even put the game in slow motion so we can see how they quickly jump between states if certain conditions are met. So let's see if we have sound. Okay. Okay, it's too loud. Just to spice things up. So, as you can see here, the AI is already in the patrolling state. So it's gone to the rightmost branch. It's the least important one. And we're currently observing the red one. It's called controller 0. But we can also switch to the blue one, which is also in the patrolling state. But it's doing different actions. So, for example, the red one but his patrolling state is designed of set of tasks. So the first task is to get a random location around it, then move to that location, and then wait for 1 second. So it's currently waiting. And the other AI is currently moving to a random location that he found, and after it reaches it, it will wait. So we can observe this in slow-mo. Let's put 0.25. So we can observe this guy going to his desired location, and then he'll start waiting. So this is how different tasks are evaluated in the behavior tree, as I said, from left to right. So right now, there are several things that can happen that will lead to this AI entering the combat state or entering the investigation state. I think what will happen now is that the blue one will bump into these little cubes on the right, and this will make noise, which will trigger the left one to go and investigate, which will break this branch here, and the red one will go to investigate, so it will quickly override this behavior. So let's see that in action. As you saw, it directly switched to the investigation state because this guy bumped into the crates, and the blue one is certainly not aware that it made noise, so he still continues patrolling. But the other one got alert and went to the location of the noise, and actually directly also even overrode this stage and entered into this branch, which is the attacking one. And it will try to do various actions like strafing, shooting, and all that. And this is an interesting moment where the blue guy is hit. So we will try to investigate the location from where he was hit. So he'll go to investigate, and he'll see probably the red one and go directly into the attack stage. And it can also evade from time to time, which is very cinematic on the slow motion. Sometimes it fails. And they both can do, as you can see, the collisions are kind of whack, but sometimes their evade works. And yeah, this is one cinematic moment. So I'll let them fight to their death, or even more interestingly, if they are low on health, as I said, the AI can go to even more important branch, which is the retreat one. So whoever goes in a certain critical health can try to find a safe location, go to that location, and start healing. So let's speed up things. Or let's see when the blue one will decide to go and hide. It needs to be hit just one more time for it to happen. But it's, yeah, so now this branch was overridden by the retreat, and it will try to move to a safe location and heal. And the rest will continue to bully him and try to attack him and stop him. So let's see that in action. Whoops. Sorry. So he'll go in behind this cover, and he'll try to heal, and the rest, what he's currently doing is that it understood that, sorry, it's the other guy. It understood that the other guy is hidden, tried to investigate, but now is just again patrolling because it lost sight of him. So this is his default behavior. So this guy will now heal and probably try to attack the other one. And they go again into the combat state. And this is pretty much it. So now the red guy will try to heal, find a cover. The other one is investigating, as I said. And it will now find the other player and enter directly into this combat state. And he will probably kill him. Oh no. Anyway, we don't have time for that. That was a very cinematic ragdoll, but so good. Where is my clicker? Is what Alan Wake said. This was the demo. I hope you liked it. Given the reaction, probably you did. So after we saw this, how are we with the time? Okay. After mothership gives me sign that I need to speed things up. So after we saw this AIs fighting against each other, which by the way wasn't scripted. Actually, this was a very good run where I could have showed you everything. But when I was doing it at home, I most of the time failed. But I just wanted to keep it random and see what happens. So it wasn't scripted. So what did we see? And what can we deduct from what we saw? So why is this in the industry not using neural networks and is still using behavior trees? Behavior trees enable the creation of enemies with predictable patterns and behaviors. And at certain points, when players analyze these behaviors and memorize them, they know how to take advantage of these AIs, and this gives them a sense of mastery and competence. And this is from where the fun factor comes, because there is a strict rule set, like in chess, for example. If you know the rule set and if you learn it, you feel that the game is fair. So in this AI, it has certain patterns, and they're very easy to observe from the players. So if now I tell you, do you want to play this game against this AI, now you observed its patterns and know what to do against it. And you kind of feel competent and masterful and will probably kill the AI. But this will happen when you iterate the game. Like 5 or 10 times you encounter combat and you learn these rules. And this is not something new, again. It's taken from a theory from a research field called game theory. And these are principles that need to be followed for a game to be fun. And this raises a philosophical question. So imagine we can design a very, very advanced AI. We can use neural networks here and train a model that maybe if you give me 5 years, maybe I can develop such a system for, let's say, for a stealth game where you need to play against enemies. And let's say, for example, this game is the new Arkham series game for Batman. You know the stealth combat there as a player, you observed it, you kind of sucked at the beginning, but in the middle of the game understood the behaviors of these AIs, and at the end you were very masterful. So what if I design an AI that is playing optimally in all these cases? And you cannot learn its behaviors, it constantly evolves. This kind of tends to eliminate the fun factor. So as developers, we need to scale it down. We need to trim this model to actually behave in a more in a way that it can be observed of a player and have some patterns in it. So you can spend 5 years developing something really advanced, and at the end of the day, you need to trim it down to something which is playable. And then why create this AI in the first place? Why don't you just use behavior trees? Because even for games like Mario, people still had fun because they observe these behaviors, and they have fun even today. I sometimes boot some old school games, some Nintendo games, and I have fun time. So we cannot really change the formula here on how a game can be fun, because game theory says so. So what did we learn so far? So each of the historical methods used for AI is very close to a pile of if-else statements, even the behavior tree. And this is okay, because game theory says so. Each iteration of AI that we saw just makes this pile of if-else statements much more organized for developers, and we can now develop complex systems. And recent advancements in AI, the things that we start the lecture with, so the neural networks, the machine learning, they won't directly change or influence these approaches that we already had. With the behavior trees or the rule-based systems, this will continue to be used. But recent advancements in AI could potentially influence other aspects of game development, and we'll see this in a minute. So this kind of concludes maybe the 99% of the games and how they are built. And I want to do just a little sidetrack of an honorable mentions for algorithms that are actually more advanced AI and they've been used in games and are not behavior trees and are actual neural networks or some other machine learning algorithm. One such algorithm is A*. It's used to tell an AI the fastest route from point A to point B, but it's not only the fastest, but the most optimal one. For example, let's say we have Baldur's Gate, and if the enemy wants to move from point A to point B, and this straight line passes through the player, it will try to avoid this player because it will trigger his reaction. So this A-star algorithm, we know, have some other rules that it can intelligently understand what is not only the fastest route, but the most efficient one, so don't get attacked or damaged. So this is used in a lot of games. It's used in Heroes 3 or real-time strategies, a lot of games like this. Then there we have the min-max algorithm. It's used for turn-based games, which are like card games, or the simplest example could be the tic-tac-toe game. So if the player makes the first turn, like makes an X in the upper left corner, then I can generate all possible outcomes of the game, all possible moves of the player and the AI, and play optimally. And it assumes that the player plays optimal as well. So you can consider it like Doctor Strange that sees all possible realities and then picks the best one for it. And this can be extended to games like chess, games like Hearthstone, and games like Baldur's Gate. But there are certain limitations, because in Baldur's Gate you cannot expand this system and be Doctor Strange and predict everything. So you need to make cuts at some point and do some heuristics that actually bring you closer to the solution. And again, we don't want the AI to be almighty. We still want to give it room for error. So that's good that we don't make it super optimal and generate all possible outcomes. And of course, neural networks. As we talked in the beginning, yes, they are used in certain narrow scenarios in games. So some horror games tried that for evolving AI, so it can monitor players' behavior and then come up with other decisions or solutions. If it sees that you tend to hide a lot, it tries to spawn enemies in corners or enemies in bushes. Or if you see that you are very scared and run most of the time, it will speed up the enemy's move speed. So things like this to bring attention is done in some very narrow scenarios. Animation prediction, for example, if you have the character is centered in certain animation, and we press the left analog stick, for example, we want to predict what's the next animation. And this is implemented for Assassin's Creed Origins. Since they had like 16,000 animations of the main character, they cannot grow this animation state machine like to be even readable by a human. So they decided that they can use AI to predict animations, which is a very nice approach. And AI neural networks can be used for training offline bots. It's done by the OpenAI, the same team behind ChatGPT. They did it for Dota 2. In 2019, they proved that they can develop in 6 months' time. I think the bot was trained for 6 months. A bot that will defeat the world champions. And hooray, they did, but this has no practical implications in the industry whatsoever. The Dota 2 bots still use behavior trees. To this day, it was just, they did it because they wanted to prove it's possible. But it's not really needed, nor it's feasible to do, because OpenAI is like a very, very advanced team of developers, and not all game developers really like to delve in this deeper into AI topics. So just a quick example of how it can be used to train an AI for a racing game. Just a little bit more. Mothership gives me another sign. I told you this lecture is long. So, a quick example. Here, a neural network is used to train this car to go and traverse the whole map of this game. It has various senses. At the first stage, it tries to do nothing, just drive forward, and it crashes. So next iteration, it tries to steer a bit to the left, and this is his neural network, by the way. And at the third iteration, it tries to steer right, and it's actually the correct thing to do, and starts to make sense of all these traces that are run here. If there are walls, what it can do, and each time it gets better and better and better, and we can run many iterations of this. And here we can see 19 cars being simulated all at once, each having different neural network at the moment, and trying different stuff, like randomly, absolutely randomly evolving, until it gets better results. So this guy here will be rewarded that it finished. So we will update the neural network and kind of reinforce it's not another generation. And at generation 50, we can see that it's learned how to drive. But keep in mind that this is only for like limited set of maps and for games that are very simple. For example, it can be done for Revolt, but it cannot be done for more complex racing games like Dirt, for example. So this was used actually in one of the Lego games, and the AI was practically unbeatable, and I raged at it. So what does the future hold? Quickly, as we saw, we are not using these new technologies, the new LLMs that are incorporated in ChatGPT. So we showed that we probably don't even need it. But one interesting topic that is currently discussed is the AI-driven NPCs. The idea is that your NPC in an RPG game can have endless dialogue options, can tell you a lot of things, and knows a lot about the world of the game. For example, if you want to develop such an advanced AI-driven NPC for Skyrim game, for the next Skyrim game, we need to train it on the lore from the previous Skyrim games. So if you ask this AI what is the stock market currently saying for Ethereum, it needs to tell you that it doesn't know shit about it. But if you ask it about something of the lore of the game, it can generate endless dialogue options. So this is something that is currently explored, but it has a lot of problems. So to run such a model like ChatGPT, we need like 400 gigabytes of video memory. So no actual computer has that, not to say consoles have only 16 gigabytes. So we can trim this model, GPT, we can trim it, and there is a smaller model called GPT-J, which yields much less promising results, but could probably be run on a PC if it's bundled with the game. But on console, it uses, again, this whole 16 gigabytes of memory that the console has. So if you ask an NPC, do you like strawberries? It will freeze all your PlayStation system, and after 5 seconds, it will tell you yes. So, so there are workarounds about it. We cannot, when we cannot really at the moment incorporate LLMs inside the games, we can probably outsource it to some server somewhere in the network, which will imply that our single-player game is now a multiplayer game, unfortunately, because it requires network, and there will be latency. But it's still possible. Then we'll have problems with voice generation, because this AI needs to respond to you, whatever ChatGPT told him, or your custom algorithm, LLM algorithm, and it will try to do some AI voice, which is kind of lacking at the moment. We are a long way from where we started, but it's still not on a AAA quality. And problem number 4, that actually we at Bloober currently are investigating if we can solve for our next game, is if we can have AI-driven NPCs that actually tell you something specific or some quests that are later executed within the game. But we have a lot of problems. Our narrative team is trying to research that sometimes the AI will yield results, like tell you, for example, there is a dragon after that hill, you can go and retrieve the treasure, but there's no actual corresponding gameplay. So programmers cannot really grasp what will users ask this AI-driven NPC, and cannot probably program everything that this AI NPC can answer. So there are like endless amount of possibilities, and as you know, if you've been on the previous lecture for Baldur's Gate, you know that players like to exploit things, and they'll certainly generate endless number of things, and programmers cannot really program these quests. They don't know what they will be. So all of this was tried and tested in a Skyrim mode, in a Skyrim VR mode, and the idea is that the player can ask the AI-driven NPC. It will call a network, call a server somewhere, a service. It will generate some voice using AI, and we will see that most of the stuff that it comes up with is practically something that you cannot actually play. So let's see.
How would you feel if I told you you're not real?
Well, that's a guard in Whiterun.
I have a clear sense of my purpose and role in this world. Whether or not I am considered real is subjective, but I am dedicated to carrying out my duties and ensuring the safety of this city. Your perspective doesn't change the fact that I have a job to do.
What would you do? Would you bully that boy too?
Bully the poor boy. Oh no, I have much more entertaining ways to handle this situation. Let's see if a sarcastic remark or a well-timed joke can diffuse the tension.
Do you know that you're in a video game right now?
In Skyrim, I exist within the world of Tamriel, not as a character aware of being in a video game. My experiences and interactions are confined to the realm of Skyrim itself. So, no, I am not conscious of being in a video game. Is there something else you would like to discuss?
What if I told you you're not real?
Well, in the world of Skyrim, I'm as real as any other character you encounter. I have my own thoughts, feelings, and experiences within the game's narrative. From my perspective, as a Nord living in Whiterun, I exist in this world just like any other inhabitant.
You're never gonna get to the Cloud District, Nazim.
And fresh vegetables for sale.
What a peculiar statement. I'm afraid you've confused me. The Cloud District Museum. I'm not familiar with such a location. Please clarify what you mean.
You don't know about the Cloud District?
Of course I know about the Cloud District. It is a place of elevated status and influence.
Yeah, as you saw, everything from the previous slide was tried and tested, of course, by some indie developers that had fun. I'm sure AAA companies will try to elevate that, but we saw all the problems like the latency in the network, the weird replies, the AI-generated voice. So, yeah. So what, I guess this has a future. Maybe we'll be able to infer in real time in the next 5 years or so. We can optimize the models for games, but still, what can we do now with LLMs if not directly incorporate them in the game? So they can help with production, I think. And I tested every one of these things that I'll quickly go to because I don't have time. I tested all of these fields and tried to design a game using only AI. So for concept art, it was quite good. So they are sorted in descending manner. So ones that will be on the bottom are the worst ones. So the concept art is the best one. So it gave me good results for different prompts, and I was I'm not good at concept art. I was able to produce something to kickstart my game as an indie, for example. Story, yeah, it behaved very well because it knows a lot of stories about movies, and you as a person cannot probably watch all the movies on the planet or all the games in the planet. You cannot play all the games on the planet. So it pulled different stories from different movies and games that I really didn't know even exist, and wrote some sort of a compelling story, and there was, again, the human factor involved. So I changed a bit the script and reprompted the model. But yeah, it's doable. There's a lot of manual work involved, but it can quickly jumpstart your story writing. Next up, we have game design. Again, same as movies and games. It can pull ideas from various places that you don't even know exist and can mix and match them and come up with some interesting mechanics. And again, you need to moderate this behavior as a human afterwards because not everything is possible. Sound, it kind of works. In terms of sound, you saw the voiceover stage that we are currently on. It can produce some sort of a useful SFX and some sort of useful soundtracks, given different prompts. There are a lot of tools that do that on the web, so it's completely free. All of this is completely free. So vocalization, yeah, it can quickly translate from US English to British English 100% correctly. It can also add some accents to the voiceovers, like Scottish accent or British accent or American accent, so you can speed these things up. And it's kind of flawless, so AAA quality we're talking here. But to directly translate your whole game to Japanese, for example, it's not sufficient. It's a good starting point, but you need to do some human work. Models and textures, very poorly. UVs are constantly getting messed up. Models are highly polygonal, so not yet there, but they're tools that are evolving. Animation is the same thing, it's pretty complex. Level design, it can pull some good paper prototypes from different games that you don't even know existed and kind of mix and match them together. So it's a good starting point for your paper prototype. So it's doable to start. VFX, very lacking. Coding, I know it's a hot topic. No, developers and programmers are not going away. At least the one that work in the games industry. If you work in the web development industry, I will be a bit worried. So, summary, quickly. Algorithms like A star, min, max, and the like will continue to be used. Behavior trees are here to stay, and they could evolve in something different, but much more organized, maybe in the future. Neural networks will continue to find more advanced applications with the games that we discussed. I am sure this will evolve. Simple games will continue to use simple algorithms, like if you design a simple game like Mario, you don't need such an evolved system. You know that Mario is fun to play even today. And generative AI, I'm sure that a lot of studios will experiment with generative AI, like LLMs, and in this will benefit the most because they'll try tools to speed up their productions. But AAA studios might fail to do so in the foreseeable future, or maybe give them another 3 to 4 years. And substantial integration for AAA titles is a bit further away, I think. So until we meet like a certain threshold where a story or voiceover is compelling. So the last thing that I want to mention is all the memes in these lectures were created by an AI. So if some of you laughed, I'm happy with that. And thanks for your time.